So we're going to start off by looking at number 31 from page 531 from your homework last night. Number 31, we're told that B, we have a triangle, and in the triangle B is equal to 4, C is equal to 6, and angle B is equal to 20 degrees. Whoops. So we're asked to determine whether the given information is going to result in one triangle, two triangles, or no triangle. And the reason for that is because this is an SSA configuration of the triangle, which is an indeterminate form in some cases, meaning there could be more than one possible answer. So let's go ahead and just draw this. So C is equal to 6, B is equal to 4. We don't know this side. And this angle right here across from B is 20 degrees. Right, so it's all based on, first of all, the angle across from the side, the side across from the angle, I should say, is smaller than the other side, right? So when the side across from the angle is smaller than this side right here, then there could potentially be two triangles. Or if it's too small, if 4 is too small, then there might be no triangles, right? Because 4 has to be, for there to be at least one triangle, 4 can be no shorter than what it would take to make a right triangle, right? So if 4 is shorter than this distance right here, between this perpendicular distance between the tip of this side C and the horizontal line down here, then we have an issue and we can't make a triangle. So that line, that distance right there, that height we call h, is just equal to 6 sine 20, right? And so 6 sine 20 is about equal to, all right, so h is equal to about 2.05, which is less than b, right, which is equal to 4, right? And that means that B is long enough that you could draw it and it can connect over there, or if you were to switch it to the other side, you could connect down there. So you could make two possible triangles, one where B is here and one where B is here, right? If B was exactly equal to 2.05, there would be one right triangle, right, that I could make, because it would be just long enough to touch the horizontal down here. And if B was any shorter than that, then we would know that there'd be no triangles that we could make. So in this case, we have two possible triangles that could result from that angle and side configuration. All right, move on to a new topic and talk about sequences and series. All right, sequences and series, the last topic that we are going to go over in this class. So we're moving on to, if you're sort of following along in your textbook, we're moving on to chapter 12. So we're going to skip a whole bunch of chapters and go right to 12 here. And so, today we're going to talk primarily about sequences, and a sequence, just to lay down the definition here, is quite simply, it's just a type of function, really. It's a function, right, where the domain is the set of positive integers. Which, another way to put that is the counting numbers, right? And so any function that has that as a domain would be a sequence. So, you know, we can define sequences using function notation. We're not going to in a second here, but we could, right? We could say f of n. We normally use n as our independent variable when we're talking about sequences as opposed to x. It's just a notation thing. And we could say like f of n is equal to 1 over n. And if f of n is a sequence, then n can only be, right, n is the set of numbers 1, 2, 3, and so on, right? And so that would mean f of 1 is going to be equal to 1, f of 2 is going to be equal to 1/2, f of 3 is going to equal to 1/3, and so forth, right? And each of these we call terms in the sequence. Right, so those are all terms in our sequence right here. Now, like I said, normally we don't define sequences using function notation like I just did in this example, but I sort of want to do it this way just to introduce you to the idea of sequences in a more familiar manner. All right, so the way we know a notation that gives us the nth term. So sometimes we call that nth term notation. Right, for a sequence. And you know, for example, that would be saying like b of n. Right, so b sub n is how we say that, and then we're going to put bracket. I'm really bad at making brackets, by the way. And we'll put brackets around that, right? And we'll say b sub n, so b is sort of our sequence, and b sub n maybe could equal 1/2 to the nth power. Right. And so that's just going to give us each individual term in our sequence, right, depending on which number term is it. Is it the first term, the second term? And that's what n is, right? That's the number of the term, if you will. So b sub 1 would be equal to 1/2 to the 1, which is just 1/2. b sub 2 would be equal to 1/4. b sub 3 would be equal to 1/9. b sub 4 would be equal to 1/16, and so forth, right? And so I can write out any of the individual terms that I want, and then b sub n is equal to 1/2 to the n, of course. That just comes directly from this formula that we have right there. So all the way out to b sub n, whatever that is. And we could keep going on infinitely, right? Or we could stop at some point. Right, so if I gave you the following formula, you should be able to write out the first, you know, defined in sort of the nth term notation here, right? And maybe it's called, this sequence is a sub n, and it's defined to be each term in the sequence is just n minus 1 divided by n. Why don't you go ahead, and so this is an example we're doing, and why don't you go write the first 6 terms of this sequence. Go ahead and write the first 6 terms. All right, so the first 6 terms of this sequence will be a sub, well, that's not going to work so great. Will be a sub 1, which is going to be 1 minus 1 over 1, which is 0, of course. A sub 2, which will be 2 minus 1 over 2, which will be 1/2. A sub 3, which will be 3 minus 1 over 3, which will be 2/3. A sub 4, which will be 4 minus 1 over 4, which is 3/4. A sub 5, which will be 5 minus 1 over 5, which is 4/5, and a sub 6, which will be 6 minus 1 over 6, or 5/6. So those are the first 6 terms of that sequence. So it just, you know, being able to just write that down is important. And so sometimes they can be defined in sort of less conventional ways. So I might have c sub n is equal to n if n is even, or maybe it's equal to 1 over n if n is odd. Why don't you write the first 6 terms of that one? So the first term, c sub 1, well, c1 is odd, so that means it's got to be 1 over 1, right, which is equal to 1. C sub 2, that's an even number, so it's just going to be 2. C sub 3 has to be 1 over 3. C sub 4 is going to be just 4. C sub 5 is going to be 1 over 5. And C sub 6 is just going to be equal to 6. So that's sort of a weird way to define a sequence, but you can define a sequence really pretty much any way you want. You have more flexibility in that sense than with a function. Although this has a similarity in that it's sort of similar to almost like a piecewise function, this particular sequence right here. All right, so being able to actually write the first 6 or 7 or 8 or however many terms of a sequence, if you're given the definition of the sequence, is important, but we should be able to go in both directions. If I give you a sequence, you should be able to figure out what the pattern is. Right, so I want you to go ahead and write out sequence formulas for the following. So I'm going to give you the actual pattern, and you're going to actually write out the formula. So, for instance, if we have e squared over 2, e cubed over 3, e to the 4 over 4, so forth. So figure out what the sequence formula is for that. We have 1, 1/3, 1/9, 1/27, and so forth. 1, 3, 5, 7. Find out a formula for the nth term of that sequence. 1, 4, 9, 16. And 1, -1/2, 1/3, -1/4, 1/5, and so forth. Right? So, write the formula for the nth term of each of those sequences for me, please. All right, let's take a look at these. So this first one here is probably the easiest one. You can see that it's just e to the n over n, right? So for this one, we could say a sub n is just equal to e to the n over n, right? That will give you any of the terms. This next one, if you notice the bottom here, the pattern we are seeing, these are all powers of 3, right? So b sub n in this case, we'll call this one b. And to emphasize really quickly, the letters here are just like we would call a function f or g or h to distinguish them from each other. We can use letters to distinguish different sequences from each other. So the b sub nth term of this sequence would just be 1 over 3 to the n, right? Just 1, oh sorry, 1 over 3 to the n minus 1, because we have to, of course, start at 1, right? And 1 is just, so at the first one here, right, we have to assume n is equal to 1 for the first one, 2 for the second one, 3 for the third one, just because that's the definition of a sequence, right? We start at 1 and we go all the way up. And so the only way we get 1 here is if we have 3 to the 0 on the bottom, because 3 to the 0 is just equal to 1, and we have 1 over 1. So we need to back this one up 1 by having the n minus 1 here. And then for the second one, when n is 2, then we get 3 to the 1 on the bottom, 3 to the 2, 3 to the 3, and so forth. The next one, it's the odd numbers. How can we write the odd numbers in terms of a sequence? Anyone think of that one? What's the difference between the odds and the evens? The odds are always off from the evens by what? 1, right? So if I make it an even and then subtract 1, that'll do it, right? Because 2 times 1 is 2, minus 1 is 1. 2 times 2 is 4, minus 1 is, is 3, and so on and so forth. So what we're doing here is 2 to the n gives us all the even numbers. 2, 4, 6, 8. So when n is 1, that gives us 2. When n is 2, it gives us 4. And then if I subtract 1 from each of those, that gives me all the odds. So start off with the evens, subtract 1 to get the odds. So that's sort of where you can think of that coming from. The next one's a little easier, right? What is that one? It's just the square of all the numbers. All it is just n squared, right? 1 squared, 2 squared, 3 squared, 4 squared, and so forth. Now this last one's a little tricky because of the alternating signs, right? So if it didn't have alternating signs, what would you call it? What would you say it would be without the alternating signs, if you didn't have to worry about that? It'd just be 1 over n, right? Unfortunately, we have the alternating signs. Is there any function that as I go 1, 2, 3, 4, will just give me 1, then -1, then 1, then -1, then 1, then -1. Can we think of an expression that does that, that switches sign? Exponential, what should the base be if it's switching from -1? Yeah, exactly. So if we have -1 to the, now to the n would make the first term negative. So what does it have to be? Yeah, it could be n plus 1. Or minus 1, it honestly doesn't matter. Just that the first term needs to be positive. So that would give me -1 squared, which is +1, then the next one would be -1 cubed, which is -1, and you have that sequence, and then you just multiply that by 1 over n, and there you go, you have your sequence right there. So that one's a little tricky just because of the alternating signs. Right, and that's another reason why you're going to start seeing exponential functions with negative bases in sequences, because it's okay for a sequence to sort of like randomly switch back and forth between negative and positive. But when we're talking about a continuous function that's defined for all real numbers and not just the even integers, then having a negative base for an exponent is problematic, right? It really is bizarre. But having a negative base for a sequence is not a big deal. It just means you're going to have alternating signs with your terms, which there's nothing wrong with that. It's just a little weird. All right, so being able to identify the pattern and write a formula for the nth term of the sequence is important. Sort of side trip right now and talk really quickly about the factorial symbol. It's not a sequence itself, but it's an operation that tends to just sort of pop up a lot in this sequences and series stuff that we're seeing right here. So the factorial symbol is just n is the is the exclamation point, right? We call that the factorial symbol, and it means something very specific in mathematics. It doesn't mean you have to yell it, right? You're not raising your voice or anything like that. What it means is, first of all, 0 factorial is defined to be 1, right? And then 1 factorial is also defined to be 1. So we have to start off with that. Those are just definitions. And then 2 factorial is equal to 1 times 2. 3 factorial is equal to 1 times 2 times 3. I think you're starting to see the pattern now. And then 4 factorial is equal to 1 times 2 times 3 times 4. Right, so you're just multiplying together the first n numbers. So if I have n factorial, that's just going to be n times n minus 1 times n minus 2, dot, 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 all the way down to 1. Right. Well, or you could do the other. Yeah, in whatever case, you know. I'm sort of doing it in reverse now, I guess. And so you can, so when I'm defining it here, I'm starting with the largest number. It's like it's like if I was doing like 4 times 3 times 2 times 1. That's what I'm doing here. I'm doing the largest number, the second largest number, times the third largest number, blah, 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 all the way down to the smallest numbers. So that's what n factorial means. But this is if n is greater than or equal to 2. So if n is 1, it's just 1, right? This definition doesn't apply. And if n is 0, it's just also 1. So we have different definitions for the first two, and then every subsequent one is based off of this definition right here. So that's what factorial means. There's certain algebraic problems. We have like 4 factorial, right? We know that's equal to 4 times 3 times 2 times 1, right? And so I could write that as 4 times 3 factorial, right? I can always, if I need to, I can pull the largest number off of the factorial and have it just be 4 times 3 factorial. 7 factorial could just be 7 times 6 factorial. And in general, if I have n factorial, I could write it as n times n minus 1 factorial. This is convenient in some instances, as we'll see later. So that's all you have to know for now. We don't have to worry about n factorial so much. Although it's important to know it is the factorial function, right? The factorial function is very fast increasing. In fact, it's faster than any function you've seen so far. So it increases faster than the exponential functions and the power functions, which is interesting. Yeah. Okay, so that's the factorial function. It'll just pop up here and there in random places. It's just important to know what the operation does. So the next big thing we're going to talk about is we've defined our sequences, right, entirely in terms of n, right? But sometimes we want to have what we call recursive definitions of a sequence. Right, this is a concept actually for those of you taking computer science with me that we're going to see in computer science a lot, is the idea of a recursive formula. So we assign a value to the first term in a recursive formula. Right? And then every subsequent term is based off the previous term. Or every subsequent term is a function of the previous term. And this can be a very convenient way. So essentially, the sequence is not just a function of what term number it is. It might be a function of that as well. It's also a function of whatever the value of the previous term happened to be. Right, so for instance, for a recursive formula, I might say the first term, s sub 1, is, let's just say it's 1 for now. And then I might define s sub n to be equal to n times s sub n minus 1. Which means in this case, we take whatever the number term we're at, if this is like s sub 2, then it's 2. It's s sub 3, and this is 3, and we multiply it by the value of the previous term. So this is one example of a recursive function, or a recursive sequence, right? And so the first term would just be 1. That's what s sub 1 is, right? The second term, s sub 2, is going to be 2 times the previous one, which is 2. The third term is going to be 3 times the previous term, which is 6. Right, the fourth term is going to be 4 times the previous term, which is 4 times 6, which is 24. And the next one is going to be 5 times the previous term, 24. And we see that sometimes these recursive functions can increase very quickly, so that's going to be 120, and so forth. So that's the first. So it goes 1, 2, 6, 24, 120. Right, it really takes off there at the end. And so this is an example of defining a sequence recursively. So once again, recursively essentially just means that the first term is just, we just say whatever the first term is. There's no formula for the first term, as opposed to just having a single definition. We have a definition for the first term, and then every subsequent term is going to be a function of the previous term and something else, which could involve n or not involve n, right? It might involve the number of the term it is, or it might not involve the number of the term. Other than that, it's still just a sequence in every other sense of the word sequence. So let me give you another, I want to give you a recursively defined sequence here, and I want you to find the first 6 terms for me. You get a, whoops, we had a little hiccup there. If you recognize this sequence and you can name it for me without looking in your textbook, I will give, well, there's no grade in this class, so I can't give you extra credit, I guess, but you can give yourself a pat on the back, I guess. All right, so the first term, this sequence we're going to just call u. So u sub 1 is just 1. And in this particular one, we're actually going to define the first 2 terms. So u sub 1 is 1, u sub 2 is 2, and then for every subsequent term, the definition is going to be u of n plus u of n plus 1. Right? Oh, sorry. This is going to be u of n plus 2 here. All right, so this is the definition we use for any term that's greater than or equal to 2. Oh, sorry, if not, that's not the case. If n is greater than or equal to 0 in this case, right? Sorry, greater than or equal to 1, my apologies. Keep messing this one up. This is sort of a weird one, but this is a recursively defined sequence, right? So essentially, the first two terms are just 1, and then the third, the fourth, the fifth terms are all just the sum of the previous two terms. So you got to sort of keep track of what all your previous terms are. So go ahead and find the next 6 terms in this particular sequence. Right. All right, let's go ahead and take a peek at this. So u sub 3, right, the third term is going to be what? That's just 1 plus 2, right? So that's going to be equal to u sub 1 plus u sub 2, right? And so you get u sub 3, once again, you get u sub 3 if you make n equal to 1, right? If you make n equal to 1, you get u sub 3, and this is 1, and this is 2. So it's, once again, it is a very strange way to define a sequence, but it works. U sub 4 then is going to be equal to, oh sorry, I actually have to add this up. So u sub 1, u sub 2 is 2. U sub 4 is going to be u sub 2 plus u sub 3, because in this case n is equal to 1, in this case n is equal to 2, right? And that will give us 1 plus 2, which is equal to 3. U sub 5 will give us u sub 3 plus u sub 4, which is going to be 2 plus 3, which is 6. And u sub 6 is going to be u sub 4 plus u sub 5, which is going to be 3 plus 6, which is 9. Right? Oh, 2 and 3 is 5. Wow, good catch there. Basic arithmetic. So we should actually have 5 there, and then 3 plus 5 is actually equal to 8. All right, so we called this is actually a very special sequence. It's called the Fibonacci sequence. You might have heard of it before. And this is just an example of a recursively defined sequence. So we've now talked about defining a sequence in two ways. We can do it explicitly, which is the first way we did it, which means one formula for each term based on n. Right, and we can do it recursively. Right, which, you know, define first term, define subsequent terms based on previous terms. But the big thing with recursively is that you're defining each term beyond the first or second one in terms of previous terms that you've calculated. So those are the two different ways to define a sequence. We'll take a break, and then when we come back, we're going to start talking about series. So we've talked a lot about sequences. We're now going to start talking about series. A series is just the sum of a sequence. The sum of the terms of a sequence, right? They can be finite, meaning we're only adding up a certain number, right? This is also sometimes referred to as a partial sum. Right? Or they can be infinite, meaning we want to add from 1 to infinity the terms, and finite just means add from 1 to some value n. Right, so you can have finite series and infinite series, which depending on what you're looking at here. And so we use a summation notation in most cases to talk about series. So for instance, if I have some sequence, right, and I want to add up all the terms, the series would just be the first term, or let's say we have some sequence which is a sub n. I'm not going to actually define it, but I'm just going to say it's called a sub n. Then the series, if that's the sequence would be the sum of all the terms of the sequence. So a sub 1 plus a sub 2 plus a sub 3 plus, and you could either go on all the way to a sub infinity forever, right? Or you could just stop at a certain value n, let's say. Right? So that's what the series would be. Just take all the terms from 1 all the way to n and sum them up. Right? Now, a more convenient and compact way to write that is to use what we call the sigma notation. Sigma notation. Named after the Greek letter sigma, right, which is this one right here. This is sigma in Greek. Right? And so the way we do this is we say we're going to add up all the terms of a sub n by putting a sub n right there from 1 all the way to n, right? What's the starting value? What's the ending value? We call these the indexes or indices, right? And so we have to refer to the index in our thing. So what we do here is we go and we say we're going to add this up from k. K is just our sort of a moving value. It's sort of like a placeholder. From k equals 1 all the way to n. Right? That means the same thing there. So essentially what this means is k is just a dummy variable. Right? That gives us the index. Right? So we call that that's our index value right there. And the index is going to go from 1 all the way up to n. So this just means make this 1, make it 2, make it 3, make it 4, all the way to till you get to n. So this is just the sort of more compact, we call sigma notation or summation notation way of expressing our series right there. So let's go ahead and work. If I said sigma of k equals 1 to 10, whoops. Let's try and actually make that look like a 10 here, folks. Close enough. Of 1 over k. And so I use k in the formula, right, wherever the index value needs to go, right? So go ahead and, if you could, write out that series in sort of expanded notation, right? Write out the series in expanded notation. And do the same for k equals 1 to 4 of k factorial. See, that's where that factorial sort of like randomly comes in. Right, so write out both of those series in expanded notation, please. Okay, so the first one here, we have, this is just 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, right, all the way out to 1 over 10. That would be the expanded version of that. And the other one is just going to be 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial. So that would be the expanded form of that, right? And of course, we could sum all these up and get an actual value. Same thing with these right here, but we're not, because it turns out we're going to try and find some easier ways to do that. That involve just using formulas instead of having to actually add everything up all the way out to n. Now, just as before with series, we want to be able to go in both directions in terms of writing out the series. Just as with sequences, I should say, we want to be able to write out the series in expanded form, as opposed to sigma notation. Right, and we want to be able to go in the other direction too. If I actually give you the series, I want you to be able to write the formula for me in sigma notation or summation notation. If I had 1 plus 2 plus 4 plus, sorry, screwed it up there. If I had 1 plus 4 plus 9 plus 16 plus blah, 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 blah. Write that in sigma notation. Actually, and we'll go all the way out to 81. So write that in sigma notation. If I had, for example, 1 plus 1/2 plus 1/4 plus 1/8 all the way out to 1 over 2 to the n minus 1. Go ahead and write that also in sigma notation. And notice the difference between these two. In the first case here, I stop at an actual number, 81. In this case, I stop at a formula. So this sort of indicates that this is going to be a finite series. And this one is, for all intents and purposes, infinite, because we haven't defined n to be any number. So it could just be infinity, for all we know. Okay, so for this first one, we see that we're just looking at n squared here, right? If n is 1, 1 squared is 1, or k in this case. K squared is 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So if I were to write that, and we go all the way to 81, so that means we go all the way out to k equals 9, right? 9 squared. And so if we're going to write that as something in sigma notation, it's going to be sigma k is going to start at 1 and go all the way up to 9, and the formula is going to be k squared, right? So it's going to be k equals 1 to 9 of k squared. Now this next one doesn't have a determinate stop. It goes all the way to n. N could be a number, and we could make n infinity if we wanted to. So it's not technically an infinite series, technically speaking, but it could be. We could make it infinite. There's no, like I said, we haven't actually defined when we're going to stop with this one. So that doesn't really change a whole lot, but it does mean that we have to just make our upper bound n. We're going to go from k equals 1 all the way to n. And they've essentially, in these cases, you're sort of given that term, right? So it's just going to be 1 over 2 to the n minus 1, which is actually kind of nice and convenient. Okay, so there we go. Now, interestingly, if we decided we didn't want to have n minus 1 in there, right? K doesn't necessarily have to start at 1. We usually choose to start k at 1, but the index can start at whatever value you want to make it start. It can start at 2, it can start at 3, it can start at 0. So what would happen, let me ask you this question, what would happen if I made this go from k equals 0 to n? How would I have to alter this particular formula here? Well, just think about what the exponent would have to be for the first term here to give me 1. What does the exponent have to be in the first term to give me 1? 0, right? So I have to have 2 to the 0. So what does, instead of the exponent being n minus 1, what should the exponent be? 2 to the n, right? So that would be the same. So these would be the same, right? These are equivalent representations of the same sequence. In this case, we plug in 1, we get 2 to the 0. Bam. We plug in 2, we get 2 to the 1, 1 over 2. You plug in 3, we get 1 over 2 squared, right? 1 over 4. And we keep getting all those. In this case, though, we plug in 0. We start at 0, and so the first term is the 0th term, the first term, the second term. Instead of being the first, second, and third term, this is the 0th term, the first term, and the second term. And we get the same numbers. We plug in 0, then we plug in 1, we get 1/2. We plug in 2, we get 1/4, and so on. So depending on how we index our sigma notation is going to depend how our series works out. So, and once again, it doesn't necessarily have to start at 1 and go to n. It could start at 0, it could start at 2. You can make it start, you can make your index start wherever you want it to. So there's a whole bunch of properties that relate to help us compute certain sequences. So properties, of series. Right, so let's say if A sub n and B sub n are two sequences, right? If A sub n and B sub n are two sequences, let's make that look like a 0 there. Whoops, wrong color. Then if I have the series from series from k equals 1 to n of c, which is just some value, times a sub k, right? So if I'm just taking this sequence a sub k and I'm multiplying each of the terms by c, right? That's just some constant value c, which I should probably write. So, and c is a constant, right? Then I can just write that as c times sigma from k equals 1 to n of a sub k, right? What I'm essentially saying here is I can take this constant value and I can pull it to the outside, right? Multiplying each individual term by c is the same as multiplying the entire sum of all those terms by c, right? Proof of that is pretty simple, actually, because we're just getting c times a sub 1 plus c times a sub 2 plus ... all the way to c times a sub n, right? And what happens if we just factor out the c, right? Right, then we just have c times that sequence, which is just what we have right there. So it's a pretty easy proof. It's just basic algebra that gets you to that point. Another property of sequences, if we have k equals 1 to n, and we have the sum of two separate sequences, a sub k plus b sub k, right? We can just break that apart, right? Because and that's another, you could do that proof relatively easily as well. Just think about the fact that you're adding two sequences together. So what's the difference if I add each of the terms up and then add those all together versus just adding up the two sequences separately and then adding those together, right? It's addition, so we know that addition is commutative. It doesn't matter what order we do it in. And so whether we add both of the sequences up separately and then add those together, or add each of the pairs of terms up together and then add it all up, you're just changing the order in how you add it. So you can break those apart easily. And the same sort of reasoning goes for if I have sigma from k equals 1 to n of a sub k minus b sub k, right? We can break that apart too. Okay, and lastly, if we have k is equal to j plus 1, we talked about this just a second ago, of a sub k, right? That's equal to, you can break that apart into k equals 1 from a to the k of n minus k equals 1 to j of a sub k. Right? And so essentially if we have where 0 is less than j and j is less than n, so j is somewhere between 0 to n. So essentially what we're doing here, right, we're starting at j plus 1 here and we're going all the way to n. We're starting at 1, we're going to n. If we subtract all the ones between 1 and j, all we have left are the ones between j and n, or all we have left are the ones between j plus 1 and n, and so we have that. So essentially it's just a subtraction. It's similar to like an area of subtraction, right? We subtract, if we get rid of all the ones between 1 and j from the whole set, right, we're just left with the ones between j plus 1 and n. Does that make sense? Right? This is the entire sequence from 1 to n of all of them. This is just the ones between 1 and j. J is some number less than n, right? If I subtract all the terms from 1 to j, what's left over are just the terms from j plus 1 to n. So that sort of makes sense. It's just a subtraction operation, essentially, with the indices. All right, so we can use these properties along with some formulas for the sum notations to be able to figure out sums of, spend a lot of time like actually adding all these up because that's extraordinarily time consuming. So there's some formulas we can use to figure out the sums for, of certain series. So as I was saying, to avoid having to add up all of these terms separately, which is extraordinarily time consuming, we want to come up with formulas for the series, right, or for the sums of sequences. Right, sometimes we call these sums of the sequences partial sums. Right, because we're going to be just adding, we're not going to add up all the way to infinity, we're just going to add to some value n. So for instance, if I have anytime I have some series, right, that goes from 1 to n, and I'm just adding up some constant, which is not dependent on k at all, that's just saying we're going to be doing c plus c plus c, right, plus c. We're doing that n times, right? We're just adding up c n times, and adding up c n times is the same as just multiplying c by n, right? So that's going to be that's just an easy formula we can use to figure out the value of this, right? Because what's the actual value of this series? What's the numerical value if I add all this up from 1 to n? Well, if they're all just constant values, I'm just adding that constant up n times, which is the same as multiplying by n. It's just the definition of multiplication. On the other hand, if I have k equals 1 to n of k, right? What if I'm just adding up 1 plus 2 plus 3 plus 4 plus and so on, all the way to n? That one has an interesting formula, and all these formulas that are going to come up, like this one's a really easy proof. We can just see right away that's the case. This one is a little bit trickier, and you can prove it without using what's called mathematical induction, but it's easier to prove using mathematical induction. But it turns out it's n times n plus 1 over 2. If I just, this formula right here will give me whatever this equals, right? This can be proven using what's called mathematical induction, which we're not going to actually get to, so we're just going to have to accept this on faith for now. It can actually be proved without mathematical induction, but we're not going to worry about the proof so much. If I have k equals 1 to n of k squared, which is 1 plus 4 plus 9 plus 16, all the way to n, it turns out that's equal to n times n plus 1 times 2n plus 1 over 6, right? That has to be proven using mathematical induction, which we're probably not going to have time to get to. But once again, just accept that on faith. So if we want to figure out what all these terms from 1 to n add up to without having to add them up, the whole thing by hand, 1 plus 4 plus 9, from all the way up to n, we can just plug it directly into this formula. So these formulas allow us to skip the monotony of actually adding up all the terms. They give us all the terms from 1 to n concisely. The last one, the formula for k equals 1 to n of k cubed is going to be equal to, and that's just once again, 1 cubed plus 2 cubed plus 3 cubed, right, all the way to n cubed, whoops, all the way to n cubed, right? That's going to be n times n plus 1 over 2 squared. Once again, that has to be proven using mathematical induction. We won't worry about that for now, but know how to use that formula. So now that we have these formulas, it's going to allow us to figure out the sums of other types of sequences. So for example, between these formulas and the properties we just introduced before, we can do that. So if I have sigma of k equals 1 to 5 of 3k, what's that going to be equal to? Right? So this, we know we have a formula for 1 to 5 of just k, but the whole 3k thing makes it a little different. But we can use the properties of these series to help break this down to something that I can solve. So if I pull the 3 out using the constant multiple property, right, I just get 3 times that sum from 1 to 5 of k, which I know that that's based on what I just talked about, n times n plus 1 over 2, right? N in this case is 5, so I'm just going to replace n with 5 here. And we'll end up with 3 times 5 times 6 is 30 divided by 2 is 15, and 3 times 15 is 45, right? And we can see that it works, right? Because if we did this out like by hand instead of using the formula, it would be what? 1 plus 2 plus 3 plus 4 plus 5. 1, that's going to give us 3 and 3 is 6, and 4 is 10, and 5 is 15. So it works, right? So we've seen that the formula does actually work, which is nice. So we end up getting right there, 45. So once again, I use the properties of series to pull out this constant multiple, and then I can go ahead and just use the formula that I know for this and then multiply it by 3 afterwards to be able to do that one. So let me give you a couple more where you have to use the formulas along with the properties to be able to evaluate what this series actually are equal to. Sums, or what the series are equal to. So if I have k equals 1 to 24 of k squared minus 7k plus 2, and I'll give you 2. All right, so for this last one, I want you to tell me what k equals 6 to 20 of 2k cubed, what that would add up to. Once again, using your properties and your formulas. Go ahead and give that a shot. All right, let's go ahead and break these apart. So this first one here, we want to start off by breaking this into 3 separate things here, right? Using the subtraction and addition property. So break it apart by subtraction and addition. Then this first part, k squared, we're going to use the formula that we have, which I actually already forgot. So, which is going to be 24 times 24 plus 1 times 2 times 24 plus 1 all over 6 minus, and then this one we're going to pull out the 7 first. right? And then, whoops, this one, I forgot to have the 2 in there. And then the sum from 1 to 24 of just adding 2 24 times is just 2 times 24, right? And so we'll end up with, for first one here, we get, this ends up being 4,900 minus 7 times, then we got to use the formula for k, which is going to be 24 times 24 plus 1 over 2, all right, plus 48. And if I go ahead and add that all together, 28, 48. This last one's a little trickier. Got to do a couple things here. First of all, I'm going to pull out the 2. First thing. Then I just have the k cubed by itself. But then I realize the index is 6 to 20, so I can't use my formulas. Only work, these formulas right here, right, only work if I go from 1 to something. So I have to use that other one that I have, which is, this is going to be the sum, and I'm just going to pull the 2 all the way out here, of the sum from k equals 1 to 20 of k cubed minus the sum from 1 to 5 of k cubed, right? You see what we're doing here? I'm subtracting off all of the terms from 1 to 5 because I only want the ones from 6 to 20. And so if I do that subtraction operation, then I can go ahead and get that. And these both start at 1, which is what I'm going for there, because then I can use my formula for both of those. So I'll have to do this on the next page then. Cube formula, I'll end up getting, right, I'll end up getting, whoops, 20 times 20 plus 1, and this is all multiplied by, was it 3? The whole thing? Yeah, it was multiplied by 3. 2, sorry, multiplied by 2. Right, all over 2, and this is going to be this, squared minus 5 times 5 plus 1 over 2 squared. Right, and we'll end up getting 87,750 for that one right there. All right, and that checks out in the calculator. And tomorrow, I haven't talked about how to use your calculator to find series, what they sum up to, but we can get to that tomorrow. In the meantime, just do it all by hand. And on the homework, right? On the homework, there's gonna be a lot of times where they're gonna ask you to use your calculator to confirm. Just skip the calculator parts where they ask you to confirm with the calculator. Unless you really want to, if you want to do some research and figure out how to use those functions in your calculator, go right ahead, but otherwise just skip them. So let's go ahead and I'll give you the assignment for tonight. And there's your homework for tonight. It's entirely off a new handout, which I will have scanned and sent out to everyone in about 15 or 20 minutes. Have a great day.